Thank you very much for the introduction. What I'd like to talk about today is some work we've been doing with the International QA Task Force on developing a comparative rating system for PV modules. And while today we're gearing it to the commercially available modules, which are mostly crystalline silicon and thin films, ultimately something like this is going to be applied to any type of PV module that's going to be sold commercially. So if I hit the button right, okay, no. I'm hitting the big green button, okay. There we go, okay. Outline of my talk. I'll start out by an introduction to give you some idea of why we're going beyond the qualification type tests that we have today. Then I'll talk a little bit about the history of the International PVQA Task Force, which we're now calling PVQAT for short. Then I'll talk about the actual comparative testing matrix that we set up, talk about how we selected the different test levels, and talk a little bit about the next steps and a summary. So, introduction, I think we all know the commercial success of PV is based on the long-term reliability of the PV modules. If modules don't survive, we really wouldn't have a business. While the modules are already the most reliable part of the PV system, it's still very important that we be looking at the continued reliability, new products, etc., because module failures can cost a lot more than failures of the other components in the system. We get a lot more inverter failures, but typically the inverter fails, takes the system down a couple of days, they replace a board or two, and up it comes again, and you're back operating. If all of your PV modules fail, you have to replace the whole system. That's obviously a much more expensive thing. Well, today most of the modules are qualified. They're qualified to one of the tests that we have, 1215 or 1646. They also come with 25-year warranties from the manufacturers. So, you know, when you're buying a product, you're assuming, hey, it's been through these tests, it's got a warranty. And those qualification tests have done an excellent job of identifying design, materials, and process flaws that lead to premature field failures. So if you look at data of the time before qualification testing for commercial modules and after, it's a dramatic shift. Before the qualification tests became standard, it was typical to have 50% modules fail in the first 10 years. Those numbers have dropped to below 1% for module types that have been through qualification. We also have another important system going on in that many of the module manufacturers today have a quality management system that is audited by a third party. Very often that's an ISO system, but there are other systems out there that are being used too. A very important piece to know that the modules are being manufactured to the same system that the ones that were tested. And then there's field experience, and I think we've all fairly convinced now that modules can survive 25 years. We've all seen numbers of them that have. All right? However, it's not all rosy. All right? It's not all good. The qualification tests were not designed to test for wear out. So the qualification test is not going to tell you whether the product you buy today is going to last 25 years. It is going to tell you it's going to last a while, but it's not going to tell you how long that is. There's also no consensus guide for QA audits of PV manufacturing. So we've seen third-party audits done very well, and we've seen third-party audits done very poorly. We also know that warranties are not of much use if the company goes out of business, and that's something that's happened a fair amount recently. Finally, we also have reports of modules whose types have been qualified to 1215 or 1646 that have failed in the field, and often well before their 25-year lifetime. Okay. So let's talk about the PVQAT. In 2011, a number of groups got together looking at those exact issues we were talking about, wondering how we could do better. And so we held a forum in San Francisco. Had about 150 people from around the world participating. And out of that forum, we established the task force, which we call PVQAT now. All right? That task force, or that forum, prioritized field failure modes that had been observed in crystalline silicon modules and established task groups to go out and look at those and try to come up with tests that would assess versus those failure modes. It also provided for creation of additional task groups, and today we actually have 11 task groups. Everything from the first one, which is looking at development of a system for the module manufacturing, through lots of different kinds of failure mode testing. And then more recently, we've added groups for thin films, for CPV, for connectors, since we're seeing a fair amount of failure of the connectors in the field. And finally, the newest one is the QA system for PV systems. So what is PVQAT? Well, it's an effort to develop a PV module rating system that meets the needs of all countries and customers. So it's a single test protocol we're looking for to be used around the world. Today, lots of people are coming up with their own test protocol for a longer term life. But if everybody has to do a separate test for a different customer, that can be very expensive. Secondly, all of the work out of PVQAT is supposed to lead to standards. So it would become a standardized system. Participation in PVQAT is open to all who want to contribute. I don't know if you realize, but most standards organizations are not open to all. You get appointed there by your national committees or different groups. PVQAT is open to all, and so far we have over 400 people participating in PVQAT. It relies on research done by volunteers, and what it is really is an effort to guide the worldwide research in the areas of how do PV modules fail in the field and how can we test for that. So there's three major efforts underway. One is the qualification of testing, or durability of testing, and that's what I'm going to spend most of the rest of this talk on. The other two are the guide for the audit for consistency in manufacturing and a new system, which is certification for system verification, called IEC TC-82. If you're interested in the last two, I have a talk on Thursday that will cover those two. But let's now go on and talk about particularly the comparative testing matrix. When we started this effort, one of the things we wanted to do was figure out how could we rate PV modules. And we started talking to the PV community, and one of the things that became very obvious was that PV manufacturers didn't want to get grades. It was okay, they said, to rate modules for different climates, but don't rate modules based on a test or something, ABC, something like that. So what we've done is to use an IEC standard on climate zones. Now that standard had about 30 climate zones, so I can imagine if we'd come up with a PV rating that had ratings for 30 different climate zones, it would be a total mess. But luckily, the IEC document had something called a moderate or temperate climate zone that combined most of the world into that one and then had extremes beyond. So we've really picked three climate zones, the moderate or temperate, and then what I'll call desert and what I'll call tropical. The other thing we've distinguished, though, is if you put a module in an open rack mount in a field, it's going to run at a considerably lower temperature than if you put it on a roof or an insulated back type system. So we're going to rate modules for both open rack and for on buildings, where it's going to run 15 or 20 degrees hotter. So PVQAT efforts have focused on determining what failure modes are occurring in the field in modules that have already passed the qualification test, 1215 or 1646. Right? If we go out there, and what we've done the last couple of years, we can actually make a list of the largest categories of failures we're seeing. And the first one is broken interconnect ribbons and degraded solder bonds, things that are caused by thermal and mechanical fatigue. The second most prevalent thing we've seen is delamination of encapsulants. In other words, the encapsulant is peeling off either the glass or the cells. And the third is the encapsulant discoloration. So what we've tried to emphasize is now looking at new test procedures that would test for those three failure modes. All right? So having identified those failure modes, we now wanted to come up with the accelerated stress test that would duplicate those. And we have a lot of history of that. So we know that thermal cycling causes broken interconnect ribbons and degraded solder bonds. So we'll use that for that set. We know that in the qualification test, we have a leg that has UV thermal cycling and humidity freeze, and that causes the most delamination of anything we see. So we're going to use that as the basis for our new comparative test for delamination. And then, of course, we also know that UV, that's wrong, typo there, the UV at elevated temperature causes degradation and discoloration of polymers. So we've used our experience to propose this test sequence. The top part is just our preliminary measurements. We have three legs there. One is thermal cycling. The one in the middle is this combined leg. I'll talk about that more in a minute. And on the far right, we have a UV materials test. So let's go on. Here's the matrix laid out with the two legs. The first leg, which is thermal cycling, we're only proposing one sequence for all six. We don't, at this point, have a breakdown of the different mounting classes or climate zones, although people have suggested that we should probably be looking at changing from our standard -40 to +85 that we do in the extremely warm roof mount. Maybe we should be running it from -20 to +105, something like that, to be more specific for that climate zone. Then for the other leg, we actually change the exposures and the temperatures, et cetera, based on the climate zone that we're in. So let's see if I can go to this side. Is this thing, I don't know how there we go. Okay, so for example, in the moderate, we do our UV exposure at 60 degrees C, while the next 4 blocks we do at 80 degrees C, but if you put it on the roof in a desert, we do it at 100 C. And then we do our dynamic mechanical load, thermal cycling, and then our damp heat that we do at the end has 500 hours for these blocks, 1,000 hours in the tropical, and when we go to the desert, we still do 1,000 hours, but we drop the humidity from 85 to 40 to be more representative of what you'd see in a desert. So let's talk about where those levels came from. The present qualification test already uses 200 thermal cycles from -40 to +85. As we've said, we've now seen significant numbers of failures in the field for product that passes that. So that tells us that we've got a problem there, but 200 thermal cycles is not enough. If we look at results of our accelerated stress tests, we find that we start seeing failures. Oops, how do I go back? I'm going to go back there, yeah. We start seeing failures in the 400 cycle to 600 cycle range, where after 200 cycles, everything is about the same. We also know that several module manufacturers over the years reported using 500 thermal cycles as an internal screen. So therefore, we chose 500 cycles with peak power current running during the process. So that's our first leg. Our second leg is to look for delamination. And if we get delamination in a humid environment like this picture, a module I took a picture of in Florida, if you get liquid moisture, liquid water, attacking the metallization of any kind of module, it's going to corrode. And that's what happened here. Well, there's a whole combination of things going out there that are making that happen. So the first thing we are going to do is to use a UV exposure, but much longer than the one that we had in the qualification test sequence. And as you'll talk about in a bit, we do have a big experiment underway under one of our task groups to actually measure how the adhesion of the encapsulant to glass varies as a function of UV exposure. And so we're looking to develop a better feel for this number. The next step is dynamic mechanical loading. The stresses in this are to stress the interfaces, and while it seems counterintuitive, we've actually seen more delamination in the field in glass packages than we have in glass polymer back packages. And we believe that's because of the higher stresses caused by having the two pieces of glass. So we're going to do a dynamic mechanical load there. Now 1215 calls for 50 thermal cycles in this sequence. We didn't show it in this picture, but we're still talking about doing it because that's also an excellent way of providing stress on the package. Humidity freeze has already proven at very, very good process for causing delamination. What happens is you pump moisture in for 20 hours and then you freeze it. Well, if there's any place in the package where there's a void, the moisture will condense, and when you freeze it, it rips it apart. Like, if you've ever had frozen pipes in your house, you know how that can get ripped apart. Well, the same thing happens in the module. And then if that has ripped apart any part of the module, then when we do our damp heat, we'll pump moisture in, and it will cause corrosion of the metals. We also know in the field that we see diode failures, and the diode tests we do are very short. They're only in 1 hour at standard conditions and 1 hour at 1.5 times the short circuit current. So we're proposing to increase the stresses in the diode by running the last 50 thermal cycles in our leg 1 with the current reversed. So in the first 450 cycles, the current is forward through the cells. In the last 50 cycles, it's forward through the diodes to stress the diodes. And then at the end of this whole sequence, we test to see if the diodes are functional. That is something that's not part of the qualification tests today. Right? And we also want to do UV testing of materials. Significant amount of analysis done by Jordan at NREL has shown that long-term degradation of crystalline silicon modules correlates with loss of short-circuit current. And much of the short-circuit current is lost because of discoloration of the encapsulants. We also have a report that in 2/3 of the papers that talk about degradation, they actually report that they see discoloration of the encapsulant. And if you go out into the field and look at older systems, you will also see most of them show some discoloration. Well, Springborn or STR reported back in the 90s that they could make that happen with a fairly simple UV test. So the group 5 of the task group 5 of our PVQAT has a large experiment ongoing right now with 5 different encapsulants, a whole bunch of different UV test chambers being measured at 9 labs around the world, and also at different temperatures, so that we can understand what the discoloration, how it's occurring, and come up with a good test to apply. So those set of experiments is going to lead to what we propose for this test sequence. So last, let's talk about the next steps. You notice there's still some question marks in here, and these are things that we need to decide on in the next year or so before we implement this as a full national standard. The first is 500 thermal cycles correct? I've heard people complain that's not enough. I've heard people complain it's too many. That tells me we're probably close. We also need to know what UV dose to put in leg 2, also what UV test to do for materials down the bottom here. What conditions we need for the UV test, whether we should put thermal cycling in the leg 2. So we've got a number of questions to be answered here. And in each case today, we've actually got work ongoing for that. In thermal cycling, we're still looking at field exposures, trying to understand how many years it takes for things to fail. We're also trying to equate field exposures with modeling and with our data. And we also need to do this 50 cycles in reverse with the diodes to see if the diodes do survive. For UV testing, we have this big PVQAT Task 5 group ongoing to provide us with the information. And we've also started to do the experiments with this combined set of tests to show how well it performs. And it's critical here that we are actually building samples that we know past 12, 15, what we think will fail in the field, so that we can show that this will identify those. In conclusion, we have a set of comparative tests that have been proposed. To move forward on the standard, the community must approve, or we need to specify the things I just talked about here. We're planning to submit this proposed sequence for its next step in the IEC process in September, so it's in next month. And we believe development of this standard is going to help provide the bankability to the PV industry, that people will accept this set of tests as a better measure of the bankability of a PV product. And if we combine that with those other two things, with the IEC RE and with the audit of the quality management system, that we'll have a much tighter and better package for people to have confidence in the PV products. Thank you.